The biggest rule when working with simplifying radicals is that we never, ever, ever want to simplify using decimals. So the way that we simplify a radical expression into simplified radical form is what I like to use, a factor tree. So take 45 and break that into any two factors you can think of besides 45 and 1. So 45 could break down into 5 and 9. What I want to do is I want to keep factoring until I have only prime numbers, numbers that can only be divided by 1 and themselves. So 5 is prime, but 9's not. 9 can be factored into 3 times 3. So once you've factored all the way, you want to look for pairs of numbers in your prime numbers. So I see that I have a pair of 3s. Any pairs that you have get to come out of the square root. So that pair of 3s will be out front. Any single numbers that were left over, like that 5, are stuck inside the square root. So to simplify square root of 45, I'm going to say my simplified answer is 3 times the square root of 5. If you want to use a calculator, it's a great, easy way to check. Type in the square root of 45, you'll get a decimal, of course, and then type in 3 times the square root of 45 and make sure that you get the same exact decimal. So that's what it means to simplify. We never ever use decimals to simplify. Let's break 80 down. Let's do the same thing. So 80 can break down into 8 and 10. Now some people may have thought like 4 times 20. What's cool about numbers is it doesn't matter. No matter how you factor them, as long as you factor correctly, you're always going to break them down into the same prime numbers when you're done. So it doesn't matter what path you take. They should all be the same when we're finished. So 10 broke down to 5 and 2. 8 can factor into 4 and 2, and then 4 factors into 2 and 2. So once again, you're looking for pairs of numbers, and only check your prime numbers. It doesn't matter about the non-prime numbers. So there's a pair of 2s, and this time there's a second pair of 2s. Any pairs of 2s get taken out of the square root, and anytime there's more than one pair like this, each set would multiply together. So I actually have 2 2s that are out front multiplied together. That single 5 is left over, and so that stays inside the square root. So my simplified answer is going to be 4 times the square root of 5. Next up is square root of 100. Hopefully right away, square root of 100 just jumps out at you as a perfect square, and you just simplify it to 10. Perfect squares are perfect squares because we can take the square root and not get a decimal, so that's just 10. Now if you didn't recognize it, watch what happens. I can break 100 into 10 times 10, and then break that into 5 times 2, and another 5 times 2. And once again, I'm looking for pairs. So there's my pair of 2s, and then there's my pair of 5s. Each pair gets to come out of the square root. So I have a 5 out, and then multiply it by the other pair that comes out. And as far as what was left over for something inside the square root, nothing was left over. That's what makes a perfect square perfect. There's nothing left behind. Okay, square root of 14, I can split that into 7 times 2, and those are both prime. There's no pairs, so nothing gets to come out. Everything just stays back inside and multiplies back together, so it just stays the square root of 14. I could say it can't be simplified or already simplified. Okay, if you want to pause the video, this would be a good time to pause and try the 3,150. The number's big, but just be careful with your factor tree. You shouldn't have any issues with it. Remember, pairs go out, singles stay in. If you want to watch it, I'll just go ahead and do it. Otherwise, I'd recommend you pause it and try it. So I'm going to do 10 and 315. I know that works since the number ends with a 0. 10 breaks down into 5 and 2, so that part of my factor tree is done. 315, I can split that into a 5 times a 63. Since I know it's divisible by 5, I just use my calculator to get 5 and 63. 63 is not prime. You may think it is, but it's not. 63 can be 7 times 9, and then finally 9 can be a 3 times a 3. So I factored all the way. You may have factored differently if you did this on your own. That's fine. As long no matter how you factor it, as long as you've done it correctly, you'll end up with the same primes when you're done. So we're looking for sets, pairs in the primes. So I have a pair of 3s right there. And I got a pair of 5s over here, so I can use both of those. Each of those comes out of the square root. Any pairs get to come out. So I have a 3 times a 5 out front. And then anything single stays inside. 2 was single, 7 was single, so they stay inside and they multiply back together. So once I simplify this, I've got 15 on the outside and then square root of 14 on the inside. We're allowed to multiply and divide with square roots. We just have to remember that when we're done, we must always simplify our answer, meaning we need to do that factor tree to make sure that we don't have any perfect squares left over. We want to make sure that we don't have any square roots in the bottom of fractions, and the biggest rule is we want to make sure that we're never using decimals. So 2 square roots can multiply together as long as both of them are in the square root. They multiply like normal, so 6 times 21 gets me 126. Now, what we're always checking for is we always have to check and see if we can simplify these answers. So I know know 126 splits into 6 and 21 since I just multiplied those together. 6 breaks into 3 times 2, and 21 can break into 3 times 7. So I see my pair of 3s. The pairs, just like before, come out, and the single numbers stay in. So the 2 times 7 are left over. They stay inside and multiply back together. So 3 times the square root of 14. As far as fractions go, I would try to simplify the fraction first. So try ignoring the square root and just do 4 over 81, see if that can be simplified. Sometimes that can save you a lot of trouble. 4 over 81 can't be simplified, but it's worth checking for. What we're going to do then is break the square into break the fraction into 2 separate square roots. Now I'm not allowed to have a square root in the bottom of the fraction, but it turns out not to matter this time because the square root of 81 is just a regular 9. I've used the square root, so it's vanished. It's just a regular 9. And square root of 4 is just a regular 2, so just 2/9 is all I have. Similar idea over here. Try to simplify the fraction 7 over 16 first. It can't be simplified, so go ahead and break it into 2 separate square roots. I'm not allowed to have a square root in the bottom, but the square root of 16 is just regular 4, so that's okay. Now, the square root of 7 is not a perfect square, and it can't be simplified. There's no pairs in there, so it stays the square root of 7. That's okay, though. I'm allowed to have square roots in the numerator of the fraction, just not in the denominator. So there's my simplified fraction. When you're dealing with numbers like this last example that have a number inside and outside the square root, multiply what's outside together. So 2 times 3 gets you a 6. And then multiply what's inside together. You can't mix and match, meaning like don't multiply something outside and inside together, but as long as you match up outsides or insides, that's fine. Before you circle it though and move on, remember we always have to be checking for ways to simplify. So 50 could be broken down to 5 times 10. And then 10 can become 5 times 2. Look for your pairs. The pairs always come out, but this time when they come out, they meet up with something already in front. As you're probably guessing, those numbers will multiply together. So the set of 5 times the 6 gets you a 30 out front. 5 times 6 is 30. And then that single 2 was left over. So my simplified answer is 30 times the square root of 2.